In this problem, what we want to do is we want to predict whether the following molecules are polar or nonpolar. And so for the first one we're going to look at iodine fluoride. So if we draw iodine fluoride, we have an iodine bonded to a fluoride. Now, there's going to be a greater amount of electronegativity between the fluoride and the iodine, such that this is going to be partially negative and this will be partially positive, causing there to be a dipole moment towards the fluoride. And so this would be a polar molecule. We can look at carbon disulfide, and we can count the number of valence electrons. So this is going to be 4 plus 2 times 6. That's going to give us 16 electrons. Carbon is going to be our central atom, and it's going to be doubly bonded to the sulfur as such. All right. If you struggle with the Lewis dot structure, you can watch some of my other videos or certainly contact me. But this is going to be carbon disulfide, and I'm going to use a different color just so you can see what's going on. But there will be a greater amount of electronegativity pointing towards the sulfurs. These two are going to cancel themselves out, and this becomes nonpolar. It becomes nonpolar. If we go down to sulfur trioxide, I've been talking too much today, sulfur trioxide, and we start counting the number of valence electrons, we know that each sulfur is going to have 6. Each oxygen is going to have 6 as well. And so 4 times 6 is going to be 24 electrons we have to keep track of. The sulfur becomes the central atom. And each one of these oxygens is going to be double bonded to the sulfur. Oops, let's put that pair right over there. So if we start counting the number of valence electrons, we have 8, 8, and 8. Let me erase those. Oops, got rid of some of the oxygen. We have 8, 8, and 8. 3 times 8 is going to be 24. And if you've taken any physics or you've dealt with vectors before, the electronegativity between the oxygen and sulfur is going to be greatest towards the oxygen. If you sum up all 3 of these vectors, what's going to happen is they're going to cancel themselves out, just as exactly as what happened up in the carbon disulfide molecule. They're going to cancel themselves out, and this is going to be nonpolar as well. We have a few more examples here. We're going to look at phosphorus trichloride. If we look at phosphorus trichloride, we're going to have 5 plus 3 times 7 valence electrons. This is going to give us 26 electrons. Gives us 26 electrons. And if we draw this out, it's going to be phosphorus plus 3 chlorides. We put the non-bonding electrons around the chloride. We start counting these up. We have 8, 8, and 8. That's 24. And so there will be a lone pair of electrons on the phosphorus. Now, what's going to happen is there's going to be a pull and electron density towards the chloride, because chloride is going to have a greater electronegativity than the chlorides will. However, because there's this lone pair of electrons, that's going to overshadow all the other ones, because what happens is this vector, that vector, and that vector are going to cancel themselves out, and this becomes polar. It's going to become a polar molecule because of that lone pair of electrons. If that lone pair of electrons were not there, it would be a nonpolar molecule. It'd be a nonpolar molecule, because the 3 chlorides would cancel themselves out. All right, now let's look at sulfur hexafluoride. Sulfur hexafluoride is going to have, we're going to need to count the number of valence electrons. So sulfur has 6. We have 6 fluorides. Each fluoride is going to have 7. So this gets us to 48 electrons. We draw the sulfur. We now have the fluorides. So I'm just putting the electrons in here so we can see, so we're able to accurately count the number of electrons in the molecule. We have 6 groups. Each group has 8 valence electrons. So we're now at our 48, and we can draw the vectors representing the direction of the dipole moments. And you can see what's going to happen here is these 2 are going to cancel out, those 2 are going to cancel out, those 2 are going to cancel out. So they're all going to cancel out in this molecule, and this is going to become now nonpolar. Nonpolar. Now we can come down here to the last example we'll have, and this is iodine pentafluoride. We start counting the number of valence electrons because ultimately we want to get our Lewis dot structure. And this is going to be 7 for the iodine plus the 5 fluorides. So this becomes 6 times 7. So this is 42 electrons. 42 electrons. We draw our iodine here, and now we're going to have our 5 fluorides coming off of it as such. I know, I make a lot of stinking dots, sorry. It's rather annoying. All right. Now we have 5 of these groups of 8, so that's 40. So there's got to be a lone pair of electrons off of that. And likewise, what's going to happen is this will cancel, that will cancel. The vertical portions of those 2 fluorides will cancel, and this fluoride here will cancel the horizontal portion, such that the fluorides in essence cancel themselves, but we have this lone pair of electrons, and so there is going to be a dipole moment in the direction of that lone pair of electrons. Because of that lone pair of electrons causing a dipole moment to occur, this now is going to be a polar molecule.